All right, we got a pretty easy lesson today on the last bit of chapter 2. So we're talking about 2.5 today, limits involving infinity. So meaning an answer could be positive or negative infinity, or my limit could be going to positive or negative infinity, right? So somewhere in the problem, you'll see an infinity show up, okay? So these are very, very easy graphical or numerical, okay? Very, very easy graphical or numerical. But we're going to look at a couple of other methods as well. L'Hopital's rule. You'll see when we have an infinity over infinity, we can use L'Hopital's rule. And we'll also look at one particular theorem that says this. The theorem says if n is a positive integer, if n is greater than 1, then the limit as x goes to plus or minus infinity of 1 over x to the n is 0. And it's a little bit hard to read that. Now there's a nice little demonstration of this using epsilon delta. Epsilon delta is a little different in this situation, okay? But I can really get you to see it graphically very easily, right? Everyone's got their homework in? Nice. I have Daniel, Grace, Anthony's not here, Marco, DeLeon, Ian. I've got all your quizzes, so and Emerson, just before we're on break, I'll get into you, okay? So this one's pretty simple to see graphically, right? And let me just keep to integers, right? If I have 1 over x, right? It's pretty clear that, right, I'm dividing, you can see it numerically even. 1 divided by 100, 1 divided by 10 billion, 1 divided by a quadrillion, 1 divided by a godzillion, right? You can see it's going to 0. It's never going to start going to negative infinity, right? So it starts to hug the line. Same thing like if I go to a higher power, right? 1 over x squared, right? Same thing, you can see it left and right going to 0, right? There's really not much to think about here at all. But I'm going to use this theorem to prove a couple of limits, okay? To demonstrate a couple of limits. So I typically don't test on this. Where are you? You're here?
No, it's the square, the green one.
Yeah, 1 over x squared. Is it getting fuzzy? Just hard to see the color, right? So we've got 2 basic problems to look at, and one is both are pretty much from calculus. Pre-calculus. So the 4 of you in here that I tortured with all that pre-cal last semester, right? These limits are obvious to us. We're talking about vertical asymptotes and horizontal asymptotes, right? So looking at, let's just look at let me just go to a new page here. Are we okay? So looking at this particular function, let's use the 1 over x squared, right? I can see that my limit as x goes to 0 from the right of 1 over x squared is what? Where am I going from the right of 0? To positive infinity. So I write positive infinity and then dne, right? So writing equals positive infinity is accepted, even though I don't agree with it, okay? So, but then we want to add in this extra feature of, well, wait a minute, but it doesn't exist, right? Infinity doesn't exist. I need a limit to be a number, right? I can also see, right, that the limit as x goes to 0 from the left is also infinity, right? And either one of these is enough to say that the limit as x goes to 0 of 1 over x squared does not exist, right? But we want this extra feature of, does it go to infinity or does it go to minus infinity, right? We want that extra little detail there, okay? So what is this deal here? This is the vertical asymptote. What's a vertical asymptote? Do you remember? What do I need to get a vertical asymptote? Something about the domain. I need a piece of the domain. Well, I wouldn't even say I need, it's not in the domain, right? The vertical asymptote would not be in the domain. But what would be the denominator? What number? 0. So 0, something over 0, not 0 over 0, right? If I get 0 over 0, we're back to, the first day of class. So if I get a number divided by 0, that's when I'm going to have a vertical asymptote. Same problem, right? Same function, but I want the limit as x goes to infinity now. Right? Now, we've already got a theorem that says that that's 0, right? Yes? So, but what are we really talking about here? What asymptote? The horizontal asymptote, right? So this one is my horizontal asymptote. And we know we have all kinds of horizontal asymptotes. If the denominator dominates, right? X squared is much bigger than the numerator 1, right? As x gets large. If the denominator dominates, I get a horizontal asymptote of 0. If the numerator and denominator are of the same power, I get a ratio of the coefficients. And if the numerator dominates, where does my function go? To infinity, right? So we talked about that quite a bit in pre-cal, right? But let's look at a couple examples of both of these types of limits. Let's start with this horizontal asymptote feature. Can I go to the next page? Everyone okay? So I want to look at something like the limit as x goes to infinity of x squared minus 2 over 3x squared plus x plus 1. Now, if you remember how we did this in pre-cal, right? We just looked at the mother function in each piece, right? So I'll say that f of x, right, is x squared minus 2 over 3x squared plus x plus 1. But I can really say in the long run that this behaves like x squared over 3x squared. Why? Because we all become our parents, right? Each of these functions starts to behave like the strongest a piece of the function, right? If you graph both of these and zoom out to the right, you would not see the difference. You'd see x squared happening, right? So right, as x goes to infinity, f of x behaves like mother over mother. I guess, some teachers don't say mother function. I like to say it because it sounds like I'm cursing, but, most teachers would say parent function. But again, wait till you see what happens. You're going to become either your father or your mother or both. So clearly this limit is 1/3, right? Now, infinity over infinity happens to be a L'Hopital rule, right? So if we look at this from infinity over infinity, if I say that f of c equals g of c equals 0, right? Don't let me zoom. Then the limit as x goes to c of f of x over g of x is the same as the limit as x goes to c of 1 over g of x over 1 over f of x. So it's just a fancy way of me of using that keep change flip piece, which you saw me do already today in that one limit, right? So, but I want to keep this in mind. Now, what do I get here? On this first one, I get a 0 over 0, right? And I'm saying question mark because you can't say equals 0 over 0, right? But what happens on the other side? Well, g of c is 0, right? So what's 1 over 0? It's infinite. 1 over 0 is infinite, right? Vertical asymptote. So I get an infinity over infinity on this side. So they're both the same. If there's anything you don't agree with, it's this piece, right? But do keep change flip, and you'll see you get exactly f of x over g of x, right? So that means I can use L'Hopital's rule here, right? Because look at what's happening to my numerator. Where is that going to as x goes to infinity? It's going to infinity. What about downstairs? Going to infinity. I have infinity over infinity here. So I can do this problem with L'Hopital's rule. So the limit as x goes to infinity of x squared minus, I forget already, 2 over 3x squared plus x plus 1 is a little hop, right? I can use L'Hopital's. So I'm doing the limit as x goes to infinity. How's everybody doing today? We okay? Of x squared minus 2 prime over 3x squared plus x plus 1 prime. I am not doing the quotient rule. I have so many times I've had students who had calculus before, high school or whatever, and they do this limit and they do the quotient rule. You don't even know the quotient rule yet. You'll know it Thursday for sure. Okay? So, but when you're doing L'Hopital's rule, you're just taking a derivative of the numerator, just taking a derivative of the denominator, reapplying the limit, and assessing from there. So what do I get? This is the limit as x goes to infinity of what? 2x over 6x plus 1. Everyone agree with that? Now I apply the limit again. So let 2x go to infinity. Well, guess what? It's infinite. What about 6x plus 1? That's infinite. So I have to apply L'Hopital's rule again. So I'm going to do a little hop. This one I don't have to do the prime symbol. I know I'm going to get 2 over 6. And of course, that's 1/3. So my pre-cal students, right, you can just see that we get our horizontal asymptote, right? Mother function over mother function. That's the way we looked at those last semester. But now we could do them with L'Hopital's rule, or we could apply our theorem, and that's what we're going to do. We're going to do the same limit one more time, applying that first theorem I talked about, okay? How are we doing? We okay? Easy, right? It's nice to have a section that's easy every now and then. If you look at my old tests and old quizzes, I might have a question on this section. I'm not planning on it on this midterm. I'm planning on not doing this section for this test. So one more time, but let's apply that theorem, right? I'm looking at the limit of x squared minus 2 over 3x squared plus x plus 1 as x goes to infinity. And I want to use that theorem, so I want to work on my function star. Everybody with me? I'm going to seek out the mother function in either numerator or denominator that's the highest power. And I see it's an x squared. So I want to multiply by 1 over x squared over 1 over x squared. So I'm going to take that highest power of any term and divide every term by it. So I get x squared over x squared minus 2 over x squared. Oops, divided by 3x squared over x squared plus x over x squared plus 1 over x squared. Right? I'm still trying to find my replacement function here, right? Of course, the worry is x is 0, right? But remember, I'm going to infinity, so I'm not worried about x as being 0, right? So it looks like, what do I get? I get 1 minus 2 over x squared. I get 3 plus 1 over x plus 1 over x squared. And there's my star. That's what I want to take the limit of. But I know, what do I know about all of those pieces with the x's in them? They all go to 0, right? So as I'm doing this limit now, right, back up here, the limit as x goes to infinity of star is now 1 minus 0 over 3 plus 0 plus 0, which is again 1/3. The algebra is kind of silly there, in my opinion. If I can do L'Hopital's rule, I'd rather do L'Hopital's rule. But I have an issue with the next problem I'm going to show you. I can't do L'Hopital's rule with this next one because of something called the chain rule. Okay. How are we doing here? We okay? So there'll be some problems in the WebAssign that you would have to graph it or do it numerically. But at least try L'Hopital's rule when you can, and at least try this method when you can. Okay? All right, let's do one more problem here, and then we'll take a little break, and then we'll start some chapter 3 stuff. Okay? We ready? Yes? So let me see if I got one here. No, I don't. Let me do one from. You don't mind if I do one of your homeworks, do you? I mean, it's not homework. It's in WebAssign, right? I got all my passwords saved. If I get hit in the head, I'm in trouble. So this is Infinite Limits, homework 8 on WebAssign. Here's the one I want to do. Square root of 64x squared plus x minus 8x. Let me just take a quick photo. So this is, I forget which problem it was. It doesn't matter, does it? Homework 8, number 4. We're looking at the limit as x goes to infinity of the square root of 64x squared plus x minus 8x. Now, look at the mother function in the radical. What's the mother function in the radical? 64x squared, right? So if I think about x getting larger and larger, I think that this thing really starts to behave like 8x, right? The square root of the mother function, right? And so now I have an 8x minus 8x. But remember, I still have to think about what's going on with x, going to infinity. So I get an infinity minus infinity, right? Even if I don't think of the mother function, I get the square root of something gigantic minus 8 times something gigantic. Infinity minus infinity. There are a few mathematicians that have studied this. All of them went crazy, but it turns out there are different sizes of infinity. So, and in this case, they are different sizes. So when I subtract them, I don't get 0. This is one of our indeterminate forms. So far we have 3 now. Actually, we have 4. We have 0 over 0, infinity over infinity, infinity minus infinity is our new one right here, and 0 to the 0, right? So, but on this one, I can see there's something I can do. I don't know how to answer this. In fact, if I do it numerically, right? If I do it numerically, I think I get 1 over 16. If I look at the graph, I see it's hovering above the x-axis, right? I'll see some kind of asymptote, right? So, but do you see what I can do? Do you see anything from our past that we could do here, that we can manipulate this? Conjugate, yes. I remember sitting in the back of the room in my calc class going, conjugate on with it. The teacher's waiting for someone to answer. I said, conjugate on with it. I know. Say again? Well, the 1 over x is interesting. But I'd get 0 minus 0. I'd get the wrong answer in this case. So it's hard to know what to do, but that's my job, right? If you see a radical, think conjugate. So what happens now upstairs? I get 64x squared plus x minus 64x squared, right? All over that conjugate, right? So it looks like my 64x squareds go away. So I just get x over square root of 64x squared plus x plus 8x. And now Yvonne, this is the right time to do that 1 over. Now, I have to look for the mother function, right? I have to look for the thing that's in charge. And upstairs I have an x. What do I have downstairs? 64x squared? So I say I don't. My highest power here is x because it's inside of the radical, right? Inside of the radical, and x squared is really an x outside the radical. So I'm going to take 1 over x over itself and distribute that to every term. You're like, how was I supposed to know? No, that's my job, to teach you what to do, right? So you gotta just go find a problem to practice. So there's one in WebAssign, there's two in the book, right? There's one on an old test, but I don't test on it anymore. So notice I distributed that 1 over x to every term, right? And so that x underneath the radical, I'm going to move into the radical. And when an x moves into a square root, it becomes x squared, right? Do you agree with that? I take that x out of the radical, move it back in the radical, it becomes an x squared, all right? You agree? It's easy to see it the other way, right? If you take an x squared in a radical, what does it come out as? An x, right? So what do I finally get here? I get 1 over square root of 64 plus 1 over x, all plus 8, and now I'm ready to take my limit. So the limit, as x goes to infinity, of star is 1 over the square root of 64 plus 0 plus all plus 8, so 1 over 16. Nice. Let's take 10 minutes. So it's 10 o'clock. Come back at 10:10. If you look at problems in 3.1, it would have something like y equals x plus 3 over x squared, and they'd ask you to find y prime, and you'd have to do some divide and conquer thing, right? So when you have a single numerator and a multi-term denominator, you can split it up into two fractions, right? So what do I get here? I get y equals 1 over x plus 3 over x squared, right? And then now I can do my shortcut. Right? So this is 3.1. It's all shortcuts, right? So what's y prime? Anybody have this one memorized yet? Yeah, the derivative of 1 over x memorized yet? It's negative 1 over x squared. And what's the derivative of 3 over x squared? Negative 6 over x cubed. Yeah. Does anybody need to see those with the power rule? Anybody want to see either of those with the power rule? Yes? So if y equals 1 over x, that's x to the negative 1, right? And y prime is bring down the power and subtract the power by 1. So negative 1x to the negative 2, or negative 1 over x squared. Right? If y equals 3 over x squared, that's 3 times x to the minus 2, and y prime is bring down the power, so negative 2 times 3. What happens to the 3? It goes for the ride. Constants go for the ride. Unless you're taking the derivative of a constant, then it's 0, right? But if I have a function times a constant, the constant just goes in or out of the limit. So negative 2 times 3x to the minus 2 minus 1. So negative 6x to the negative 3, or negative 6 over x cubed. X to some power, right? You're doing that. Unless the power is 1. X to the 1, we know the derivative is 1, right? mx plus b. So 3.1's not a bad section to look at on your own if you want more practice than shortcuts, okay? What are the shortcuts we know? Let's just recap our shortcuts real quick. Do you need me to go back? Let me know, okay? I'm not in a rush. Go back. Not in a rush. We're ahead of the game, actually. If you look at the schedule, I wasn't supposed to do product quotient rule till Thursday, but we're well ahead of the game. The Tuesday before the midterm, we review. The week before the final, we review. So for the midterm, I have a 1-class review. For the final, I have 2-class review. What are our shortcuts we know? If y is a constant, right? Then y prime is what? 0. If y equals mx plus b, y prime is just the slope, m, right? The derivative is the slope. If y equals x to the n, y prime is n times x to the n minus 1. If y equals e to the x, y prime is e to the x. And we have all these memorized, right? You're going to have them on your formula sheet, yes? If y equals ln of x, y prime is 1 over x. If y equals sine of x, y prime is cos of x. I might do that one today, prove that one to you. If y equals cos of x, y prime is negative sine of x. You remember my wheel there, right? Right. Oops, sorry, I got my alphabet wrong. From sine to cosine, there's no negative. Derivative of sine is cosine. From cosine to sine, there is a negative, right? Derivative of cosine. This one? Yeah. Y is sine of x, y prime is cos of x. Cosine, this is cosine. If the function is sine of x, the derivative is cosine of x. Yvonne, you asking? Yeah? Yeah, we'll have more. We're going to keep adding to this list, right? We're going to have the other trig functions that should all be memorized, right? The tangent, the cotangent, the secant, the cosecant. Then we're going to have the inverse trigs memorized. I typically leave everything as ln, base e, log base e. I don't usually use the other log functions. So your quiz on Thursday is going to be, give me a tangent line of one of these on my list, right? And I want to see a curve, and I want to see the point, I want to see the tangent line and the graph, rough sketch, right? Yes, your calculator you can always use, your TI 8384, yep. So, I mean, you know it's coming, so I'm saying we don't need a formula sheet for the quiz. I'm going to see what you do without the formula sheet on the quiz. But then the formula sheet I'll let you have on the midterm because it's a big exam, right? It's a good chunk of your grade, too. All right, here we go, 3-2. We've got a product and a quotient rule. I'll probably just try and leave it at the product rule today. I'll probably just do the product rule today, and we'll start quotient rule next time. We'll see. I got a little bit less than an hour. It might be too much for our human brains to handle all of it today. But basically, I'm going to have a product or a quotient as my function, right? So if y equals f of x times g of x, it's obviously a product. I'm multiplying two functions, right? And then my quotient rule has got to look like f of x divided by g of x. So a quotient, dividing, right? A fraction. I remember hating the quotient rule so much when I was learning it, I would just turn it into a product. I would bring that bottom function up, raised to the negative 1 power, and do everything with the product rule. But then I started teaching it, and I said, well, there's got to be a nicer way for me to figure out how to remember this formula. And so I use a loop, okay? I eventually want you to be able to do it without a loop, but I've got two loops, but I've always set it up this way. I take my first function and my derivative, my second function and the derivative. So for both of these, product rule and quotient rule, first function and derivative, second function and derivative. Yes, you with me? And then I'm going to get the letter P here with a positive inside, and the letter Q here with a negative inside. So you can see my product rule and my quotient rule. So my product rule is f g prime plus g f prime. So you can see my my product, multiplying on this diagonal, and then multiplying and adding and multiplying on this diagonal. You with me? The quotient rule is gf prime minus fg prime all over g squared. So, but it's the numerator that I'm really focusing in on, right? So this is definitely going on your formula sheet. Yes, you with me? I have a loop for the chain rule too. I'm just trying to do anything I can to make the chain rule easier. So product rule, quotient rule. All right, let's do an obvious example. A couple obvious examples, and then we will do a not so obvious example. And this is the part where the algebra starts to get pretty damn messy. Okay, so you've got to make sure that you're staying organized. Okay, stay organized, keep things clean, take your time, baby steps, make sure you factor at the end. Everything should be completely factored at the end. Diego, let me know, okay? Nice. All right, we'll do it. An obvious one first, okay? So I've got y equals x squared. Product rule or quotient rule? It's a product. It's x times x, right? But of course, this is, I got a shortcut for this one, so I don't need it at all, right? What's y prime here? 2x. Okay. But I'm going to do it as a product now, right? Like I said, this one's obvious, right? So I can really see y as x times x, right? So my first function is x. My derivative is 1. My second function is x. My derivative is 1. You with me? So you see how I'm setting it up? Right? You can see how I'm setting it up. First function derivative, second function derivative. I got my loop going here, right? So if y equals x times x, y prime is x times 1 plus x times 1, right? I'm doing this product, x times 1, f times g prime, and then plus this product. And obviously I get 2x, right? So it seems like it works. I'll prove it today, but it seems like it works. Let's do another one that's obvious, okay? We ready? Next one. So y equals x minus 3 times 2x minus 3x squared. Now, obviously I got a product, right? But I can shortcut this, right? We can shortcut this one, yes? Because they're all polynomials, right? So I can expand this out. What do I get? I get 2x squared minus 3x cubed minus 6x plus 9, help me, 9x squared, right? So negative 3x cubed plus 11x squared minus 6x. So my shortcut says what? Who's got it? negative 9x squared plus 22x minus 6. So again, I'm just trying to demonstrate that this thing works with something that we know already how to take a derivative of, right? But we're going to do one in a second that we don't know how to take a derivative of. So here we go. What's my first function in the product? It's x minus 3, right? What's the derivative of x minus 3? 1. Everyone agree? The second function in my product is 2x squared. Sorry, 2x, what is it? Yeah, 2x minus 2x minus 3x squared. And that derivative is 2 minus 6x. So what do I get for my product rule here, right? I get y prime is x minus 3 times 2 minus 6x plus 2x minus 3x squared times 1, but who cares, right? Yes, Grace. Grace, where are you? Oh, okay. Yeah, so we're doing the same problem over now, right? With the product rule. So I'm seeing that my first function is x minus 3 in the product, and my second function is 2x minus 3x squared. I take the derivative of both of those, and then look at that loop, right? The loop is the product of this diagonal, right? And then this diagonal. I'm sorry, Grace, I just can't hear you. Just one more time. Oh, the f prime. It's the derivative of x minus 3, right? So y equals x minus 3 has a slope of 1, right? So I'm doing shortcuts there, right? What's the derivative of the 2x? It's 2. What's the derivative of the 3x squared? 6x, right? Power rule on both of those, yes? So I'm going to simplify this. I get 2x minus 6x squared minus 6 plus 18x plus a 2x minus 3x squared. I get a negative 9x squared from these two. I get a 22x from these three minus 6. Same answer. I do want to check if that derivative is factorable. It's not. So I'm going to leave it as it is. But if it was factorable, I'd want to factor it. Cool. Let's do one that's not so obvious. Okay? And I'll sneak the chain rule in here too. Can I go to the next page? Yep. No, I'm in no rush. Nice. Let's do a product rule that's not so obvious. Y equals sine 2x. It turns out that this derivative, well, notice first of all, what the inside function is. What's the inside function? 2x. When the inside function has a derivative that's not 1, I must do the chain rule. What's the outside function? Sine of x, right? So it turns out that the chain rule will give me the derivative of the outside function evaluated at the inside function times the derivative of the inside function. We're going to learn this next week, okay? So don't panic about it. Outside function is sine of x. So the derivative is cos of x. Leave what's inside. Then multiply it by the derivative of the inside function. The inside function is 2x, derivative of that is 2. This is the chain rule. But I want to do this with the product rule. I want to show you that I get the same derivative by using the product rule. So I got to make this, is this sine times 2x? Is that the product? No, please don't ever write down your paper. Don't ever think of this as sine times the argument, right? Sine is a function. The inside argument is another machine inside of the machine, right? But I can use an identity here. Y is 2 times the sine of x times the cos of x. You need all of those trig identities. If you had me for pre-cal, you know which ones that you need to know. If you have that textbook, that first blue page, I typically don't use the tangent identities, except for tan of x is sine of x over cos of x. That's the only one I use. But the half angles, double angles, sum and difference formula, only sines and cosines with those. So we're ready to take our derivative. Our first function we can call 2 sine x, right? What's our derivative there? What's our shortcut we know? Cos x, yeah, so 2 cos x. Remember, constants come for the ride. So the identity from pre-cal class is this, right? That's a trig identity that you either have to have memorized or put them on your formula sheet or both, right? In case you have a panic attack during the test and you don't remember if you're remembering it right. So derivative of sine is cosine, right? So derivative of 2 times sine is 2 times cosine. Yes, you with me? Second function is cos of x. And what's our derivative there? Negative sine of x. Everyone okay so far? Well, how do we know those are true? You're memorizing them right now. Go ahead, Ivan. Yeah, and I chose that function. It's the identity. It's the identity from pre-cal. You should have it memorized. I can show you where it comes from after class if you want to, okay? So, but right now, all your trig identities should be memorized. And that's a lot, right? It's a lot. So that's why I'm giving you the formula sheet. It's hard to memorize everything. All right, product rule. So what's my y prime? It looks like I get a negative 2 sine squared x plus 2 cos squared x. Do you agree with that? I'm first doing this green product. 2 times a negative is negative 2. Sine times sine is sine squared. Right? Everybody okay here? I want to put these in a different order and then factor out the 2, right? So I'm going to factor out a 2, and I get cos squared x minus sine squared x. And my students from pre-cal from last semester should know this identity. Cos is 2x. So y prime is 2 times cos is 2x. And that's what we wanted. That was from my chain rule piece. Yeah, we okay? Nice. So you saw a couple of these trig identities, right? Probably freaked a couple of you out. Just make sure you've got those trig identities on your formula sheet, and you'll see them. They happen all over my tests. So just right, just jump into that product rule. Those problems. Um, I think I have a review sheet for chapter 3 too. I don't remember. So. All right, let me prove this. So you don't have to write it, but I would like you to agree with the steps, okay? So proof. Let y equal f of x times g of x. We know that f prime of x is going to be the limit as h goes to 0 of f of x plus h, times g of x plus h minus f of x times g of x all over h. Yes, yes. F prime is same as y prime. F prime of x is, yeah. Yep, same thing. Y prime. F prime of x, y prime of x. We know we want that loop, right? But I'll show you that we have the loop after, okay? So the way I do this is I add 0. I think this is the first time you're going to see me add 0. So I've got f of x plus h times g of x plus h. Don't tell me. I forget. Give me a second. I guess I should have wrote it down before I did this, but it's okay. I think I need an f of x, so minus f of x times g of x plus h. Yeah, that's what I need. So I want to add 0. So you see there, the red pieces cancel, right? So I've got a multi-term numerator and a single-term denominator, so I'm going to split them up into 2 pieces, into 2 fractions, right? I'm going to split them up into the green piece and then the other piece. So I've got f of x plus h, g of x plus h, minus f of x times g of x plus h, all over h, plus the rest of it, f of x, g of x plus h, minus f of x times g of x, all over h. Right? Common denominators. I'm just undoing, and we do a lot of this in this classes. All of the things we used to do to put things together, we take them apart now. I like to call this one divide and conquer. I'm splitting a fraction into 2 fractions, right? Well, it looks like I can factor, right? What can I factor out of the first one? I can factor out g of x plus h, right? So I'm going to do that, right? I've got f of x plus h minus f of x all over h times, right, g of x plus h. And notice what I have in my parenthesis there. It's the derivative, right? When I take the limit as h goes to 0, I'm going to get f prime there. And the other one I can factor out in f of x. And what I have left is what's going to be my g prime. Right? So I'm going to switch the order, and then I'm going to take my limit. So I'm going to do the limit as h goes to 0 of f of x times g of x plus h minus g of x all over h plus the limit as h goes to 0 of g of x plus h times what eventually will become my f prime. Right? So it looks like I'm ready to take my limits. I get f of x times g prime of x. Right? You can see my diagonal now, right? Can't you see it? That loop? Right? Product loop. Top. Plus g of x plus 0, right? There's an h there, g of x plus h. The h goes to 0 times f prime of x. So there it is. Y prime is f times g prime plus g times f prime. Yep. Easy, right? Just got yeah, where are you here? This one, yeah, I see it. I see where it's nasty. X plus h here. Now, do you have to do something like this on a test for me? No, right? But you should agree with everything I did. How the hell, Robert, how the hell was I supposed to know to add 0? I only know because my teacher taught me. Right? And then I went to university and took Advanced Cal 1 and Advanced Cal 2, where I proved everything in calculus. So, horrible. I loved it, but it's horrible. So, but you don't need to, you just need to be able to use the product rule right now. That's it. Let's do another one. You ready? Almost. Okay, I can wait. I'm in no rush. I can tell you this, I am psyched for spring break. I'm ready for it right now. What week are we in? Week 4? So 4 more weeks. Week 4, 5, 6, 7. And then spring break. Yes. I tried to get them to create a fall break, but they wouldn't listen to me. Thanksgiving is almost a full week, but they should have just made it a full week, in my opinion. Joanne, tell me when, Kay? Of course you can. Of course you can. Of course you can. Shake it like a Polaroid. Yeah, there's the first page of it. Is it clear enough? But Joanne, you know you're not responsible for the proof, okay? Okay, I got you. And now here's the second page. Yep. Joanne, you got it? First page? Yeah? Nice, let's do another one. That's not obvious, but you're going to see that it entails some algebra, okay? So here we go. Where am I? There I am. So product rule with this extra piece of algebra. Now remember, you're going to have all these answers in the back of the book, all the odd answers I gave you, right? You're going to do the problem, most likely correct, but you're going to have a different answer than the book. I want the answer from the book. So you're going to have to do some algebra. It's usually an LCD. It's usually clearing fractions. Sometimes it's a conjugate. Sometimes it's factoring. It's the same thing we've been training you for since 8th grade, maybe even 7th grade, maybe even before that, right? We've been doing this stuff also. This calculus is easy, right? So it just takes a little patience, right? So let's do y equals e to the x square root of x, right? That's my function. It's clearly a product. Yes, you with me? We might as well do a tangent line with this one too, right? So let's get our derivative with our product rule here. So first function is e to the x. Do I know this derivative by heart already? Yeah, e to the x. This is a pretty magical one. Second function is square root of x. And this was on your homework you just turned in. Derivative was 1 over 2 square roots of x. Does anybody need to see that with the power rule? Anybody want to see that derivative, that shortcut derivative? Let's have this one let's have everything memorized. Right? Product rule is going to come from here with a plus sign. So I'm going to get y prime is e to the x over 2 square roots of x, right? You see that product there, yes? Plus e to the x square root of x. Everyone okay here? This is where you're going to stop, and then you're going to go look at the book, and you're going to realize, oh, I see they have a single fraction. Right? So I know I need a single fraction. So all I need is an LCD here, right? You could also think fractions within fractions. Do you see fractions within fractions? That's when you know you have to do something, okay? And we'll ease up on this a little bit in Calc 2. When we're undoing derivatives, we tend to not care too much about factoring, but when we're doing derivatives, we want factors. Why? Because when things are factored, I can solve for 0. I can let the numerator be 0 and solve. I can let the denominator be 0 and solve. Right? When the numerator is 0, I get horizontals, tangents. When the denominator is 0, I get vertical tangents. So I can see here I need an LCD of 2 rad x. So I'm going to multiply my second term by 1. Right? You see, I'm trying to get my denominators to match. So I get, what? E to the x plus 2 e to the x. Oh, sorry, 2x e to the x, right? Yes, exactly. So I got my single denominator now. But make sure you notice over here, right? Make sure you notice this. 2 times an e to the x times an x, right? Rad x is x, yes? So I get 2x e to the x. Still not done, because I can factor upstairs, right? So I get an e to the x times a 1 plus 2x all over 2 square roots of x, and there it is. So there'll be a lot of that. There'll be a lot of that. Wait, how'd they get that? And then the trick is to first do your work again, right? It's hard to see a mistake. So it's probably better just to do the derivative again, And if you get the same thing you got the first time, then you're thinking, I got to do some algebra. Okay? Sometimes we do second derivatives. In Calc 2, we do fourth derivatives. So now I take a derivative again, and they get pretty messy and they get pretty long. Right? So just try and be patient with it. Be organized. Right? Practice a lot. The reason why I'm pretty damn good at watching TV is because I do it every day. You want to practice a lot. Let's do a tangent line here. What's my domain of my original function? Positives and 0, right? What about my derivative? It's my domain of my derivative. I can't use 0 anymore, right? Can't divide by 0. Can't put negatives in, can't put 0 in. So at x equals 0, I have no slope. In fact, it's vertical there. It's that face plant where my skis are straight up in the air, right? So let's get the tangent at 1. So I need a point and I need a slope, right? So I know that y is going to be e to the 1 times square root of 1, right? And to my original function, so that's just e. Yes? And I need my slope, that's going to be y prime at 1. So that's e to the 1 times 1 plus 2 times 1 all over 2 square roots of 1. So it looks like 3e over 2. Everybody know what I'm doing here. I need a point, I use the original function. I need a slope, I use the derivative. Everybody okay? Everybody with me? I'm ready, right? To get my equation, right? I've got the tattoo. What's my tattoo? Y minus y1 equals m times x minus x1, right? So I've got y minus e equals 3e over 2 times x minus 1. I could go into Desmos with this, just as it is. So maybe I do that before I keep working on it. Can't put it in my calculator like this. I could add e to both sides and put it in my calculator, but I want to make it look as pretty as I possibly can. I get 3e over 2 times x minus 3e over 2, and then I'm going to add e. Adding e is the same as adding 2e over 2. So I get y equals 3e over 2 times x minus e over 2. mx plus b. We want that final answer to look like an mx plus b. Sometimes the book doesn't write it as an mx plus b, but you should write it as an mx plus b and the way they write it. Just verify that you can do some algebra to get their answer as well. Right? We ready? Desmos, yes? Yep, say again? Yes, yes. Let me put line numbers, okay? And then tell me where you want me. Where do you need me? Ian, okay? All right, I'm ready for Desmos. Here we go. So my original function, y equals e to the x times square root of x I had to point 1 comma e. Did I? What point did I have? Oh, e to the x, not e squared. Sorry. There we go. 1 comma e. Can you see the vertical tangent at 0? Can you see how steep the hill gets there? And our tangent line was y equals 3e over 2, right? Times x. Oops, 3. Geez, 3e over 2 times x minus e over 2. Yeah. Right? Yes. I got skills. What line?
Just 12 to 13. I don't know why. I think I feel like it would be or it's negative. Never mind. You're all
Yep.
Why adding e to
Just getting a common denominator for this piece. For the b.
at number 3?
Line 3?
Yeah, 19.
Yep.
Multiplying
By 1 in the form of what I need for the LCD. Right? So this one's already got a denominator of 2 red x. So I need to get the other one to have the same denominator, but I'm only allowed to multiply by 1. Only that second piece, because the first piece has what I want already. All right, let's look at one more thing today and then quit, okay? So you got homework, you're going to be ready for the quiz, you're working on your formula sheet, right? You got plenty of things to practice on WebAssign. You should be looking at Chapter 2 tests, because you can do a Chapter 2 test. Your midterm, the midterms that are there, you can only do some of it right now, because I mix a lot of 3 into Chapter 2 stuff, okay? I want to look at a quick proof of y equals sine of x implies y prime is cos of x. So we're going to prove this real quick because we have everything we need to prove this. We're ready to prove this. In fact, we were ready last week. So I'm going to look at f prime of x, right, as the limit as h goes to 0 of what? Yeah, sine of x plus h minus sine of x all over h. Everybody with me? I did put this proof on as an extra credit once, but I've kind of gotten tired of extra credit. It's usually the students that can get the extra credit don't need it. And the ones who can't do it need it. Right? So I just trying to grade less. That's all. I'm going to work on star, which is sine of x plus h minus sine of x all over h. And I'm going to use my sum, I'm going to use my identity for sine of alpha plus beta. So we have an identity on that second page of your textbook, sine of alpha plus beta. And that is sine alpha cos beta plus cos alpha sine beta. Alpha and beta, first two Greek letters, that's all. Alpha, beta, yes. So I get the sine of x cos of h plus sine of h, cos of x sine of h minus sine of x. Sorry, I ran into here. All over h. And you say, well, Robert, am I supposed to know that identity? Yes, you did it in pre-cal, but you can put it on your formula sheet, right? It looks like I can factor, right? Do you see where I can factor? I got a sine x repeated twice, so I'm gonna divide and conquer with those two terms. So I've got sine x cos of h minus sine x, all of that over h, plus cos of x sine of h all over h. And this kind of looks like the hyperbolic sine, the cosine function cosh or sinh. So I want to make sure we don't confuse it with that, and make sure you see that x and h are my arguments. Well, I already said I can factor, so let me do that. And so in the first one, I can factor out a sine of x, and I get cos of h minus 1 all over h. And then the second one, I'm going to write it as cos of x times sine of h over h, right? And you can kind of see where I'm going, what I'm going for. On that right-hand side, sine h over h as h goes to 0 is what? 1. So then all I have to, right? So I got cos times 1. It turns out that the first piece is going to be sine times 0. I'm going to show you that this limit right here is 0. So I'm ready. This is my star, right? So I'm saying that the limit as h goes to 0 of star is sine of x times the limit as h goes to 0 of cosine of h minus 1 all over h. Notice I don't care about the limit of sine of x. Why? Because there's no h there, right? Plus cos of x times the limit as h goes to 0 of sine of h over h. So I'm gonna say that here I get sine of x times 0 plus cos of x times 1, but I have to prove to you still that one limit, right? Provided the limit as h goes to 0 of cos of h minus 1 over h is 0, right? I have to still prove that. But that's pretty easy to prove with L'Hopital's, right? It's just a limit here. You see, if I plug in 0, I get 0. I get cos of 0 is 1. 1 minus 1 is 0 upstairs. And if I let h be 0, I get 0 downstairs, right? So I'm really getting the limit as h goes to 0 of the derivative of the numerator, which is what? Negative sine of h minus 0 over 1, right? I'm taking a derivative with respect to h, right? Do you see that? That's my variable now. So derivative of sine of h, cosine of h is negative sine of h. Derivative of 1 is 0. Derivative of h is 1. And now I can just plug in, right? So I just get negative sine of 0, which is 0. Nice. Have a great day. Everyone turned in homework, yes?